in this problem, what we are asked to do is we are asked to determine the reaction forces for A, as well as the tension in this cable BC. And we are told that we have this member BA. This member has two different forces that are being applied to it. And this becomes a 3D rigid body equilibrium problem. For a problem like that, we then need to write down the equations we have to use. So we're going to want to use the sum of the forces in the x are equal to 0, the sum of the forces in the y are equal to 0, and the sum of my forces in the z direction are equal to 0. Additionally, because it's rigid body, we're going to need to use moment equations. So we're going to have the sum of the moments about the x-axis are equal to 0, the sum of the moments about the y-axis are equal to 0, and the sum of the moments about my z-axis is equal to 0. All right, so now that we know the equations we need to use, let's draw a free body diagram of this problem. So for this problem, first I'm going to draw this member, and my member is going to look like this. This is AB. And I'm going to draw in my applied forces. So I'm going to have a force that goes straight down, and that's my 400 Newton force. I'm going to have a force that's in the x direction, and that's my 200 Newton force. Okay, so I have a tension force from BC. So when I cut the rope, I know it's going to go from its in tension. So it goes from B to C. So I'll call this tension BC. Now the only other forces I have are my reaction forces at A. And this is a little tough because of the type of pin and rod and collar that this is. So we're told this is a square rod and collar. What this does is this eliminates any type of rotation about any of the axes, right? If this was a circular rod and collar, then it would be allowed to rotate about that z-axis. But the square rod and collar does not allow any rotation about that z-axis. So that means I'm actually going to have a reaction moment in the z direction, a reaction moment in the y direction, and a reaction moment in the x direction. Now, additionally, I'm going to have some reaction forces. Now, how is this constrained? Well, I can't move along this y direction. I can't move along this x direction. I could potentially, if I wasn't in static equilibrium, I would be allowed to move along this y direction. So this means I'm going to have a force that's some ay. I'm going to have a force that's some ax, and those are all my reaction forces. So let's put them on my free body diagram. I'm going to have a force that's ax. I'm going to have a force that's ay, and I'm just assuming they're in the positive direction right now. And then I'm going to have a moment, reaction moment. So I'm just going to call that mx. I'm going to call that my, and I'm assuming they're in the positive direction of rotation. And then I'm just going to put a little dot up for the z axis, and I'm going to have a moment about the z, a reaction moment about z. Okay, so now I've drawn my free body diagram. I have all my forces. I need to now sum the forces in the x direction. So let's start with that. If I sum the forces in the x direction, this is equal to 0. Well, the easiest one to do is this ax, right? I have an ax force. It's in the positive x direction. So I'm going to have ax. Now, I most likely have some force that's along this cable. So I need to figure out what components this cable has. So this cable needs to be a force along a line. So if I remember the equation for force along a line, the vector form is the force is equal to the magnitude of the force times some position vector over a magnitude of that position. So if I translate that to this problem, this position vector is going to be this position vector BC. to do that, I need to figure out what these coordinates are. So B, what is this coordinate? I have to go 3 in the X, I have to go 0 in the Y, and I have to go down 1 in the Z direction. In the C, I go 0 in the X, I go 1.5 in the Y, and I go 0 in the Z. And those are the positions of this of points B and C. So now if I wanted to say, okay, let's figure out my vector BC and my position vector BC, what I need to do for this position vector BC, and let me throw this arrow back in, I need to figure out what is this position vector. And I need to subtract the tail from the head. So if this is position C over here, and this is position B, and I just call this RC and RB, then my position vector RBC is RC minus RB. So this is going to be equal to, all right, RC minus RB. So minus 3I, 0 minus 3, then 1.5 minus 0, so plus 1.5J, and then 0 minus 0 minus a minus 1, so minus plus 1K. Okay, so that's my position vector. The magnitude, RBC, is going to be equal to the square root of minus 3 squared plus 1.5 squared plus 1 squared. So let's bring our calculator up and let's figure this out. Minus 3 squared plus 1.5 squared plus 1 squared. Take the square root of this. And we get this is equal to 3.5. Okay. So now let's just write out our final force along a line. We're going to have this force along a line, which is TBC. TBC is equal to TBC. This is the magnitude. This is what we don't know. Times minus 3I plus 1.5J plus 1K over 3.5. All right, so now we know that we have some x component. This is going to be minus, what is 3 divided by 3.5? 0.857, so 0.857 TBC is equal to 0. Two unknowns, one equation. Can't do anything with this right now. Let's keep moving on with our equations. The sum of the forces in the y is equal to 0. All right, so again, I'm going to have this TBC equation. Let's do my reaction forces first. So I have AY. Then I have this plus 1.5 over 3.5. So plus 0.429 TBC. And then I have one of these forces, so plus 200 is equal to 0. Okay? Still don't know what TBC is, so keep going. I have the sum of the forces in the z direction is equal to 0. Okay, the z direction, I don't have a reaction force in the z direction. I have a minus 400 for this force right here. And then I have plus, what's 1 divided by 3.5? 0.286. So plus 0.286 TBC is going to be equal to 0. So I can solve this. I can say, okay, 400 divided by 0.286 The 400 went to the other side of the equation. And I get this is roughly 1400 newtons. So do this in a different color. TBC is 1400 newtons. Okay, that's good. Now I'm going to back substitute this here, and I'm going to back substitute this here, and I'm going to get what AY and AX are. So here I'm going to have AY plus 0. Let's do it a different color just to break it up a little bit. So AY plus 0.429 times 1400 plus 200 is equal to 0. And let's solve this. 0.429 times 1400 plus 200. Then we'll say that's 18. We'll say that it's 800. So AY is equal to 800 newtons. All right, and we'll do the same thing over here. We'll say AX minus 0.857 times 1400 is equal to 0. 0.857 times 1400. And that's what AX is equal to. So AX is equal to 1200 newtons. So let's star this. This is some of the answers that we need. These are my reaction forces and the force along the cable force. So now I need to sum my forces because I still need to figure out what my reaction moments are. So I need to sum my moments about the x-axis, and this is going to be equal to 0. Now remember, if a force goes through the axis, or if it's parallel to the axis, it does not exert a moment on that axis. So let's look at the sum of the forces in the x. Well, 200 and 400 both go through the x. All of my forces in the A go through the x, right? AX is parallel and goes through. AY goes through when it goes through. Now TBC, what forces do I have in TBC? Let's actually draw this. So I'm going to have a minus force going this way. That's my x. And in this case, x is going to be parallel. I'm going to have a plus 1.5. 1.5 is going this way. Let me draw it in black. 1.5 and a plus 1. So 1 is going this way. Okay. I'll draw this one in black too, to make it easier to see. So this z is going to go through my x-axis. This x right here is parallel to my y-axis. So the only forces I have that create a moment about my x-axis is going to be this y component of my tension. So my y component of my tension is going to be 0.429 times 1400. And then I do need to still put in the reaction moment. So plus my is equal to 0. Mx plus mx is equal to 0. Now, when I rotate about this x-axis like this, it's going to be positive because it's going to rotate about that axis. It's going to rotate head first. Okay, so we can calculate this. And if we calculate this, we're going to have 1400 times 0.429. And this is going to be 600 Newton meters. So mx is, when it goes to the other side of the equation, it's going to be equal to minus 600 Newton meters. So that all that means is the sense of this moment right here, mx, is actually going in the other direction. Okay? So now we go to the sum of my moments about the y-axis. and that's equal to 0. All right, so in the y-axis, well, 200 is parallel to the y-axis, so it doesn't exert a moment. 400 is not. 400 will exert a moment if we rotate our entire problem through this y-axis right here. What we get is the 400 is going to turn head first. So it's going to be 400 times this perpendicular distance, which is 3. And then we have TBC. What forces of TBC do we have? We don't have this y component because it's parallel. We have the x component and the z component. So the x component is going to be positive, and it's going to be plus. The x component is 0.857 times 1400 times 1. That 1 is the perpendicular distance. If I extend this out, that perpendicular distance to the y-axis right here is 1 meter. So that's my x. My y component is going to be a minus, and because if I rotate this, it will rotate tail first. And this component is 3 meters away, so it's going to be 0.286 times 1400 times 3. All right, so that's all of the forces, because again, all of my A's for all of these go through the origin. So it goes through all 3 of these axes. Okay, and I just can't forget my reaction moment plus my is equal to 0. Okay, let's put this in calculator. So 400 times 3 plus 0.857 times 1400 times 1 minus 0.286 times 1400 times 3 is roughly 1200. Bring it to the other side of the equation and I get my is equal to minus 1200 Newton meter. I think that's still on the screen. Nope. So let's just move this over just a little bit. Okay. Now finally, I need to do the same equation with the z-axis. So the sum of the moments about my z-axis is equal to 0. Okay, what's going to be a moment of the z-axis? Again, let's look at all of my forces. The 400 Newton force right here is parallel with the z-axis, so it's not going to have a moment. The 200 Newton force is going to create a moment. The perpendicular distance is this 3 meters. So if I rotate that positive, it's going to go head first. So I'm going to have 200 times 3. All right. And what's happening with this tension force right here? So the up force is parallel to the z. The y force, or this x force, is actually going to go through the z-axis. So that's not going to have a moment. And this y force is going to create a moment about the z. Its distance to the z-axis is 3 meters. It's going to be positive, so I'm going to have plus my y force, so 0.429 times 1400 plus the moment about z is equal to 0. And we can solve for this. 200 times 3 plus 0.429. So I forgot this distance right here. This distance right here, I think I said it, is 3 meters. So I still need that 3. So 2400 mz, my reaction moment z, is equal to minus 2400 Newton meters. Now, all the minus sign means for any of these is that the force or the reaction moment is in the opposite direction. So what this means is this moment of Z right here is actually it's going this way. Moment of X is actually going this way. Moment of Y is going this way. This is positive. This one should have been negative, right? Yeah, that should have been negative, and this is positive. So AY is actually pointing in that direction. So hopefully this video has helped you learn how to apply the equations for 3D rigid body equilibrium to figure out what reaction forces occur in a problem.